good evening to you. Let me share my screen. We're going to be looking at forces, how you can resolve forces and find the resultant of forces. Now, this could be a straightforward thing. I don't know. Could be a straightforward thing. I know that there's one particular diagram that people simply find almost impossible. Some people just cannot get their heads around one diagram. I'll show you what it is later, obviously. But this thing about forces crops up all over the place. It's not just mechanics. It can be in electrons moving in field. It can be all sorts of things. Okay, so it's a very, very useful skill to have, to be able to apply it in places which are unexpected, unfamiliar. That's a word that the exam board use, unfamiliar. So we've got to nail this thing, got to absolutely nail it. If you think you're perfectly okay with it, that's great. That's great. I mean, hang along and let's see if there's any bit that I say which takes you a little bit further in your understanding. So while we're waiting for a few people to turn up, here we have the an exam question from an English exam. I love putting these in. I love it because you lot, I know that you lot are sitting there. No, I know what. I know that you lot were maybe on the 24th of August when your GCSE results came out. If you are in year 12, you went, thank goodness I don't have to sit through another English lesson in my life, or another history lesson, or a geography lesson, or whatever. I'm being slightly rude now, obviously, but this to me sums up English. It is so interesting, and I just can't do it. I can't get my head around it. How could I possibly analyze text A? First, got to do is read text A in an exam. That's going to be difficult enough for me. And then analyze it to explain how it uses language to create meanings and representations. I don't know. And then there are 25 marks for that. How anyone can mark it consistently, I don't know. If you give it to one marker and then another marker, they should give exactly the same mark. They should do, because we have to be consistent in our marking of A levels. But I bet you £1 billion they don't. But in physics, they are almost spot on. You can't go wrong in physics when you mark it. It's either right or it's not right. And you know full well when you are taking a test or doing an exam or whatever, you know if you are on the right lines, especially if it says, show that the acceleration is almost 6 times 6 meters per second squared or something. You just know. It's a completely different way of thinking. It's a different discipline, and I love it. That's why I love it so much. Okay, so if you see a question like that, that clearly has got something to do with, well, there's projectile motion, there's a bit of horizontal stuff and a bit of vertical motiony stuff. Yeah, that's probably got something to do with components. This one, guaranteed, just look at it. That sort of question, you look at it and you go, right, I'm going to need to use some trig in that question because I need to work out something. I've got to create a triangle and work out what the forces are. If you have something like this, exerts a force on the wing of a bird, apparently. Which does that? Apparently. So you know full well that you're going to have to use some trig and draw some triangles. Okay? Again, if you see the word resolve, if you see the word velocity, or any other vector quantity, you know that you're going to have to use some trig. Now, I'm going to start really patronizingly simple. I hope you don't mind. Because when I looked at one exam question and then went on to the examiner's report, which is what you all do, they said this. Now, this really surprised me. Weaker candidates tended to be confused by idea of vector components, and it was not unusual to find the inclusion of the word horizontal and the word vertical to be confused. Okay? Now, I've realized this only recently. If English is not your mother language, then you are at a slight disadvantage. I don't know yet what Russian is. for horizontal and vertical? I'm going to look it up because I want to know. I want to take an exam in Russian just to see what happens, just for fun. Okay, so we know what horizontal is. We know what vertical is. I know it's a bit patronizing, but look, some people can't do that. But you are not the weaker candidates. You're way up there, guys. Right, here's something else. Look, I don't know. Oh. The uniform magnetic field has got an arrow on it. That smells of a vector quantity to me. So this question, even though it doesn't really instantly leap out at you as being a resolving a vectory sort of question, does have some vectory stuff built into it. Now this is an obvious one, and this is the diagram that people find quite tricky. Some people go, nah, I can't do that. Okay, so I'm going to try to give you a foolproof method of being able to draw something to do with that diagram. Again, in electrostatics, we're going to have to do something with vectors. In raindrops, we're going to have to do something with vectors, and there's the diagram. Okay, that is a diagram, and we're going to learn how to draw the forces on that block. Okay, it's remarkable how many different diagrams I've seen of the forces drawn of that block. In equilibrium, just add that there, in equilibrium. Okay, let me move that there. Hold on, I'm just going to put this, if you don't mind, over there so I can just see. Oh, come on. A bit of that. Okay, let's see what's going on. Right, so we are not going to do the resultant force and resolving forces as advertised in our presentations. We aren't doing that because, why have I put that there? I don't know. If you do an OCR, you've got to make estimates of physical quantities listed in the specification. So any forces, any vectors that we use, you're going to have a vague idea of how big they are. The same in EdXL and the same in AQA. You've got to make some guesses, some estimations. So let's start with a lovely GCSE question. It's really important, I feel, for all of us to start solid with some solid foundation so we can all build from that. Okay, here's a GCSE question. Are you joking me? Are you joking me? Okay, and I'm not going to ask you to answer that question. I'm not going to ask you to answer it, but I think you know. Okay, I think you know. That's a foundation GCSE question, probably question 1. Okay, 1B maybe. Now, this is what we're going to not do, because as I've said, it doesn't just work for forces, it also works for vectors. We are going to find resultant vectors and we're going to resolve vectors. Now, you know what all the vector and scalar quantities are because it's in the specification. Now, I really like AQA. I really like EdXL. Because not like OCR that just says, yeah, you've got to give examples of each. AQA and EdXL actually give you the example. So these are the go-to safe bets. Okay, that EdXL one is let me just check that. Is particularly interesting because it's got, okay. Oh, no, it tells you. Scalars, mass, density, volume, energy, power, work, speed, and distance. Yeah, okay, they tell you. Vectors, displacement, velocity, acceleration, force, and weight. Notice they do not have pressure in there. They do not have time. So don't risk putting those in either scalars or vectors. Do they have direction? Do they not? Who knows? I don't care. Don't even think about putting those in, because they're a bit contentious. So we're not having those. Okay, okie dokie. Right, let's have a look. So there is an A-level question. Back to A-level questions. Okay, now you know because you've seen the list. Here's another A-level question with some answers. There it is. Do I like that sort? Maybe I do. I don't know. Give an example of a vector quantity and a scalar quantity. Well, from part A, A vector quantity has magnitude and direction, whereas a scalar quantity only has magnitude. That's the perfect answer if I say so myself. So giving one example of each, there you go, you can just get it off the list. Part C, we are going to come back to that later. I'll just leave it on there. I'll just let you think about that for a minute. Based on what we did before, based on that GCSE question. So let's have a go. Let us start with finding the resultant vector. Now, what I could have said, instead of finding the resultant vector, I could have said, let's instead add some vectors to find the resultant vector. Okay, so we're simply adding vectors. And what we do when we add them up is we get the resultant vector. So forgive me, I'm going to do some maths now, and I'm going to do this. I am going to find the 2a plus b. So there's a minus 4 minus 1. 1, 2, 3, 4, minus 1. Two of those. 1, 2, 3, 4, minus 1. So there we have the vector 2a, boom, like that. Okay, there's my vector 2a. And onto that, we are adding b, which is 3 across 1 down, 1, 2, 3 across 1 down, which is there. So there is my b. So the resultant is going from where we started to where we end up. We end up with this. If I just draw it in like that. So that is my resultant, which I hope this is going to work, is 1, 2, 3, 4, 5, minus 5, 1, 2, 3, minus 5, minus 3. There it is. Okay. That's kind of it. That's kind of it. In a different disguise, that's it. Okay, so let that sink in. And then we're going to look at some more and then have a look at some actual quantitative ones. A and B are drawn on a grid. A is that, B is that. B in terms of A, well, I'm not going to do it, but there's our little trick. They are in opposite directions. So B in terms of A, B is, well, it's twice as long as A, so the magnitude is twice as big, but it's going in the opposite direction. So B equals minus 2A. All straightforward. The chat is silent. I'm expecting that to be good. Everyone's happy with that. Moving on a little bit, we've got this. On the grid, no. Okay, you can do that. C plus D, you can do that. Okay, let's have a think about what happens if we add these vectors. Okay, I'm going to add this vector going up in this direction, and I'm going to add it to a vector going from the same point in this direction. So it's starting at the same point and it goes in that direction there. Now, I hope you realize and remember that when you did your adding vectors at GCSE, the beauty of a vector is you can put it wherever you like. You can slide it around. It is a translation. It's moving from one place to another place, and it doesn't make a blind bit of difference where you start. So what I'm going to do is I'm going to slide that red one up to, oops, that should have been a straight line, up to there. Okay, because that is the same length, same magnitude, it's in the same direction because it's the same vector, see, and it goes up like that. Now, the resultant of those two is that, starting at the beginning and to the end, that is the resultant vector. Could be the resultant force, it could be the resultant displacement, it could be the resultant velocity, could be the resultant acceleration, it could be any resultant vector, not just forces, could be any resultant vector. Okay, now here's the beauty. We are going to look at GCSE questions which were all on one line. They were collinear. Okay, but at A level, they think that you can cope with coplanar vectors, vectors on a plane. Now, if you do that, you can, there it says, vector triangle, not just forces, vector triangle to determine the resultant of any two coplanar forces. Now, if you want, you can do it by calculation. If you don't want to do it by calculation, you can draw a scale drawing, and they will give you enough space on your paper to do a scale drawing. They might even show you a scale drawing. It will tell you what scale to use or whatever. It will help you on your way. Okay, so long as you have a 30-centimeter ruler, a brand new shatterproof, see-through 30-centimeter ruler, and a gorgeous new helix protractor. Okay, so you can draw any scale drawings that you like. But when it comes to a vector triangle, if you want to calculate it, and I'm gonna say you can do this if you are really confident, but what they do is all exam boards, I think, give you, that's definitely OCR, they give you the sine rule and the cosine rule. So if you are confident with those, and please make sure you are confident with your cosine rule to find out what the value is. Now, there is a triangle which relates to the cosine rule. The angles are in capital letters, the sides are in little letters. The side A is opposite angle A, side B is opposite angle B, side C is opposite angle C. So that's the nomenclature. So I think you can see how we can use that. If we are trying to find this vector here, let's say we are trying to find this vector here, the size of that guy there. If we know the other two and the angle between them, so we're trying to find the size of the length of A. If we know little c and we know little b and we know the angle between them, then we can use that. It's a bit like Pythagoras. A squared equals b squared plus c squared. Good old Pythagoras there. But there is that little bit added on, minus 2bc cos A. Now you can see if A is 90 degrees, then cosine A is 0, and that term disappears, and it turns into the Pythagoras' theorem that we all know and love. A squared equals b squared plus c squared. Okay, this is making it ever so slightly complicated. You can do that if you like, okay? But make sure you are confident with that. And what the exam board say, the examiners say, the higher achieving candidates use the cosine rule. But there are hardly any questions there where you can apply that. But it's there if you want to. Right, let's have a look. So what we're going to do is this. We are going to add two vectors. Okay, now using my favorite Walter Fent simulations, here they are. Okay, so what I've done is I've started off with the GCSE thing. Okay, I've got a diddly one going over to the right and a longer one going over to the left. Now, when I click find resultant, what's going to happen is the left hand vector is going to slide along. So the start of the left hand vector is at the end of the right hand vector, and it shows you what the resultant is by a little red arrow. That's the resultant. Okay, so let's just think about this. The left hand one is bigger than the right hand one, so the resultant is going to be to the left. Okay, let's have a look. Oops, find out our resultant. There we go. So off it goes, and there's our resultant. Okay, now if we do this, if we take it from GCSE and turn it into A level like that, now I'm going to do it something like that, a little bit like those maths questions I gave you before. Now, these are vectors. They could be forces, they could be accelerations, they could be velocities. I don't care. Right, here we go. Watch what happens to the left-hand vector. It slides over there, stops there, and that is a resultant. I'll try to do it. Let me try to do it a bit better than that. Let me try to do it like that just for the sake of it. I think you will know why later. So those are my two vectors. I tried to do it, but I got it slightly wrong. Those are my two vectors. I'm going to do that, and there is my resultant. Okay, so even if we have two vectors going off in weird directions, different sizes, different directions, the resultant of those, let me do it again, the resultant of those just happens to be, there it is, a red arrow pointing vertically upwards. Right, now, let me show you what I mean by that. If I have my little elastic band like this, with my little mass, and I put my little mass, I'm very, very good at this, and put my little mass in between, let me see, can you see that? There we go. And put my little mass in between the bits of elastic and pull it down. At the moment, nothing's happening. It is in equilibrium. The two forces, due to the tension of the elastic bands, are pulling up at some odd angle, one to the left, one to the right. But I can feel that I have to keep it in equilibrium, pull it down like that. So if I release it, the downward force disappears, and then there are two forces acting on it. The pellet doesn't know that. The pellet hasn't a clue what's going on. It doesn't know there are two forces acting on it. It only feels one force, the resultant force. So that resultant force, which is acting vertically upwards, makes it do that. Okay? That is how this works. Let's carry on and look at what happens if we apply Newton's laws. Okay, now, just an extra thing here. Newton's second law, I've got to clarify this a million times. The more times I clarify it, the better I feel. Newton's second law is not F equals ma. It is not, okay? What he actually said was, I'm going to cut through all the messing about and tell you what he said. He said, the force is proportional to the rate of change of momentum. I'm going to write this down. This is a good place to do it. F is proportional to the rate of change of momentum. That's what he said. We didn't actually, but that's what he meant. Okay? He didn't know what momentum was. He just called it motion. But that is kind of what he meant. Now, we can thank the French for this, because what they have given us is the Système International, the SI unit of measure. That is so lucky, because that makes the constant of proportionality 1. Only if you use SI units, okay? Then that we know is mv minus mu over t. Now, only if m is constant, then F equals m v minus u over t. Only if m is constant. Okay, if it's like a rocket burning fuel or a car burning fuel, then the mass is not constant. The thrust of the engine can be constant, but the mass is not. So we got to think about that, and that makes life slightly harder. But usually the mass is constant. So I can take the mass out of the bracket, and we recognize v minus u over t is the definition for acceleration. So we can get that. But that's only if m is constant, and only if m is and only if we use SI units. Now, if you have a sense of humor, and instead of force in newtons, we use force in pounds. Okay, pounds is a force. I'm sure you've come across pounds, stones and pounds. And instead of meters, we use feet. You know, the foot's about 12 inches. It's about that long. I'm sure you've come across that as a unit of distance. And we're sticking with seconds. Then F does not equal ma. If we have the weight of something, the weight equals mg. Well, it doesn't, because in SI units, we've got to have a constant, because if it's not in SI units, we must have a constant, because the constant is not 1, and that constant is 32. So that makes life very unpleasant for us, and our equations become unwieldy. So SI units, the way forward. Okay. Oh, the second mark for Newton's second law is, and the rate of change of direction is in the direction of the force. So off, we're going to do these laws again, but I'm going to do this now because it's important. State Newton's law, 2 marks. Newton's second law, 2 marks. Force is proportional to the rate of change of momentum, 1 mark. Second mark, and the rate of change of momentum and the change of momentum is in the direction of the force. Kind of obvious, but that's the second mark they are looking for. So we've got our forces now. We now know that this thing is going to accelerate if there is a resultant force. Now, I'm going to go back to my little diagram here. I'm going to draw, not with my ruler because I can't be bothered. I'm going to draw a force like that, and I'm going to draw a force like that. And we saw, if I draw the forces slid around as we saw in the diagram, then the resultant force is going to be that. If though, like my doingy elastic bandy guy, if I get rid of that, 1, 2, 3, and do that, bom, 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 then, bom, 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 then I know that that body is in equilibrium. Okay, I know that if I put my pellet here and have it being held by 2 forces of elastic going in that direction and me holding it down in the red direction, I know full well that that is in equilibrium and its velocity will be 0. It will either stay there or it will carry on going in a constant speed in a straight line. That's Newton's first law. Okay, there is a way of showing that, which I hope you have done, or if you haven't done this yet in year 12, I hope that you do it. Or if you don't do it or haven't done it, I hope you will appreciate what I'm about to show you, because this is how it can be shown. Okay, it is, I think it's in, I can't remember which one it is. I should have checked it. I think it's in AQA, and it's the, I've forgotten what they call it, a force board or something like that. This is how it works. You have a vertical slab. It's the worst experiment in the world, by the way. It's rubbish. It's rubbish. But for the sake of argument, we're going to try it and assume that it works. So what we have is we have 3 masses, 1, 2, and 3. 1, 2, 3. So I think that has got a weight of 3 newtons, I think. So this force down here is 3 newtons. 1, 2, 3. That force up there, so that's 3 newtons because it goes around the pulley. That is 3 newtons, and this looks like, I can't see, 1, 2, 3, maybe 4 newtons, I don't know. So that could be 4 newtons like that. So you set it up with your 3 newtons, 4 newtons on it, and you leave it to equilibrate, to stop jiggling around. Okay, now, if it is stationary and not accelerating, we know that this point here is in equilibrium. So if we look at the 3 forces acting on it, they will form that triangle like I showed you before. But the way you do it now, this is the sort of thing where you really need to pay attention to when you are doing experiments and know how to make them better. Because when I did it, I always left some little plastic mirrors on the front bench just to see if anyone would use them. They never did, but that's not surprising. I don't care. The way that you do it quite accurately is, you can see somebody here putting the mirror, sorry, I'll do this in black, putting the mirror against the paper like that. And the string goes in front of it. Now, because the pulley is the way it is, the string is about 1 centimeter or so away from the paper. So when you draw the direction of the strings, that's what you're supposed to try to do. When you draw the directions of the strings, it's quite tricky to get your eye perfectly perpendicular to the paper, but not if you put a piece of mirror behind it. Then it's easier to get your eye more or less perpendicular. What you do is you look at the string and you close one eye and you move one eye backwards and forwards like that, and you'll see the string, you'll see the string in front and the image of the string moving backwards and forwards. If you arrange your eye so the string and the image of the string are lined up like that, you know that your eye is perpendicular. So then what you can do is do this. You draw a line like this and a line like that. On the other side, you do a line there, and a line there, and a line there, and you put a blob on the paper as close to there as you can get it. Then you take it all away, and then you draw your scale drawing. So you could then, so you've got this. You've got your directions like that, and you've got your 3 newtons. Now you can use a scale of, I don't know, 5 centimeters to a newton or something. So you draw a line up here, 15 centimeters long, and a line up here, 15 centimeters long, and a line down here, 4 newtons, 4 times 5, is 20 centimeters long, like that. Now, with a shed full of luck, if you do this, so I'm going to do the top one in orange. If you go like that, you can see this is rubbish. You can see this is rubbish. Let me do that a bit better. If you draw that, that's a bit better. If you draw that parallel to that and that parallel to that, you should get your lines crossing up here, and that should be equal and opposite to that. Okay, you can do it on the other two as well. It should work. It doesn't, it's rubbish, but it's sort of vaguely close and vaguely satisfying. Okay, that is sort of using that apparatus does appear in questions because it is on one of the specifications. I think it's AQA, but you are going to check. Right, let's have a look at this, because my good friend Walter Fent has done a cheeky little algorithm like this, and it works. It works. So just pause there and wait for you to notice something which you are going to like. Oh, no, you're not. No, you're not. Left, right. Oh, I'm making that 4. I've made that 4. Okay, that's it. What? 3? Hey, what? Hey. Okay, first of all, it doesn't matter where these are. The triangle of forces stays the same. 3, wasn't that a 3, 4, 5 triangle? Oh, I'm sorry. I made it 3. I can make it a 3 newtons or 4 newtons. And you know that that's a Pythagorean triplet. So they're at 90 degrees. There you go. 37 plus 53 is 80 is 90 degrees. Okay. But it does show you the forces. Okay. And with this, it's important to see that it doesn't matter where you put this stand like that. You move these about up here, wherever, the parallelogram always stays the same because the forces are in the same direction and the strings will arrange themselves so that you get that right angle triangle. We can, if we want, mess about. Let's make that 7 newtons. What? Why didn't you do it? Why can't I do that? Hey, why can't I do that? Hey, why isn't it letting me change it? I don't know why it's not letting me change it. What's going on? There's no reset button or anything? I'm surprised that I can't change it. Oh, yes, I can. 3 newtons, 5 newtons. I don't know why it's doing it now, but there you go. Fiddle around with that. Have a look at how those forces are pointing to give you the triangle which satisfies the relationship. Okay? Right. Let's go back to my PowerPoint. Let's go back to my PowerPoint and get rid of that and have a look at, so we've looked at that. That works nicely. We've looked at the parallelogram of forces up there, and we can see how drawing those forces enables us to find the resultant. So the resultant of the blue and the red one is the pink one. Spookily, the resultant of the pink one and the red one is a blue one, and the resultant of the pink one and the blue one is a red one. It doesn't matter which triangle you use. So that is the resultant. So let's have a look at some questions. Okay, so all we have to do is add these forces up. So if I draw it over here, I'm going to draw, well, there's my balloon. The up thrust, sorry, this is going to be embarrassing, so I got it wrong last time. The up thrust is 10,200, like that, but the weight is 9,800 minus 9,800. So just thinking of the vertical component, yeah, that's nice. The downwards force is 400 newtons. I could have done that in my head, but I would have got it wrong and that would have been embarrassing. Now, the wind is the horizontal force. That's all there is. So we don't have to do any adding up or whatever. So I'm just going to leave that in as 300 like that. And you've got it. We've got ourselves yet again a little Pythagorean triplet, 300, 400. So we know that if we take the like that, we know full well that that is a 500 Newton force. So the force acting on the balloon is 500 newtons. Wrong. Wrong, wrong, wrong. The magnitude of the force acting on the balloon is 500 newtons, but I'm just taking this question an extra stage because there is a second thing you have to say about vector quantities. It has magnitude and it has direction. So what we could do is say, calculate that angle at an angle of cos to the minus 1, 0.6, I think. Okay, you've got to work out what that angle is. Usually they say at the bottom of your page, it says F equals newtons and at an angle of degrees. So they tell you, but sometimes they don't. And you've got to be careful. For any vector quantity, you have to give both the magnitude and the direction. Oops, daisy. Here's one which you, where is it? Ah. Right. So that is the question. And if you want, in your heads, I can see what you're doing. I can see what you're doing. You are doing that. You are constructing yourself a parallelogram and you are trying to work out what that is. Well, I do not fancy doing that by trigonometry. I can, if you want. If you do that, then that, I'm not doing that. I'm not doing that. I'm going to do what they want because on the next page, there is that. There is a blank sheet of graph paper and you are expected to draw a scale drawing. Now, there's a little diagram at the top. Now, cheated. The dots aren't on the graph paper, by the way. I did that so I don't make a fool of myself. So I'm going to draw the 400 newtons. There it is. There's my 400 newtons at a scale of one big square there is 100 newtons. Okay, so there's my scale, whatever that is, 2 centimeters or whatever. 2 centimeters is 100 newtons, 1 centimeter is 50 newtons. That's my scale. And then I reach for my protractor that I did not forget to take to my exam. And I do that, same scale, measure the 60 degrees. There it is. And then I draw my parallelogram like that and like that. And then I find the resultant like that. And then I take my ruler, measure its length, find its length, convert it to a force using the scale, and then job done. And then measuring this angle here, maybe, yeah, I'm going to measure this one. I can then work out the angle to the horizontal. I could have worked out that angle to the vertical. Doesn't really matter. Your choice. Pardon me. So that's how you do it by scale drawing. Sometimes they make it blindingly obvious what you're supposed to do. Okay, so if that is the case, and for this printing on the page, I can't do it on your screen, obviously, but the 1.8 Newton is 9 centimeters long. So you've got to work out what the scale is. 0.2 Newtons per centimeter. Is that right? Yeah, 0.2 Newtons per centimeter is the scale there. And then you've got to complete the scale drawing to find the magnitude of only the magnitude, notice, just the, so you do this, ba-boom, ba-boom. No, you don't. You do that, kind of, and then you find that, ba-boom, ba-boom. You measure its length. You use a scale to convert it back to newtons, and then it's in newtons, yes, and then you find the magnitude of it. It's not interested in the direction, so don't bother with that. Okay, if we have something like this. Okay, here I have a free body diagram. Like that. We can see that. I'm going to leave this out for a minute because this involves resolving vectors. So I'm going to leave this out until we've done resolving vectors, and then I shall come back to it. Okay, let's move on. So we've got all of these things. There's our OCR data booklet with the sine and cosine rule in. There's the cosine rule, which we might use if we like. Okay, now we could have done this. Okay, just check the time. So I'm not going to do this. But when we got as far as this with our projectile motion, the question carried on and asked us what is happening to the cannonball when it strikes the water. So we have worked out that the cannonball is in the air for, so the first thing we always work out is how long it is in the air for by using the height dropped. S equals ut plus a half at squared is our go-to calculation. The vertical velocity, and I'm going to be a bit of a pedant now, I hope you don't mind. The vertical displacement that it has fallen is minus 67 meters because it's gone there and it's gone downwards. Upwards is positive, downwards is negative. So it has gone minus 67 meters. What is its initial horizontal velocity? 0. It's going along, granted, but its vertical velocity is 0, so that goes. It's not a quadratic, we can relax. It has got, there is a half. The acceleration is the acceleration due to gravity. Okay, so that is where our minus signs are in agreement. They cancel out. So we don't have the square root of a negative number. Everything's fine. The universe works. And then you find t, okay? We are given how fast it's going. How fast it's going. Doesn't tell us how far. Oh, it will do. It will do. We need to know how far. This is projectile motion. We need to know how fast it is fired at. Well, we know that it does 150 meters in whatever time is we get from that. Don't know what it is. That gives us our horizontal velocity of our cannonball. That remains fixed. Oh, come on, let's just do it. Let's just do it. 67 times 2 equals, divided by 9.8 equals, square root of answer equals, come on, really? Oh yeah, 1.9 seconds. Okay, so it's taken 1.9 seconds. So the velocity of this thing is it takes horizontally, S over T equals 150 over 1.9 equals 150 over 1.9, 150 divided by 1.9 equals, what, really? 79? Okay, 79 meters per second. So that is what, really? I'm not sure about that. That is what I think its horizontal velocity is. Anyway, let's check. And then you find its vertical velocity. And then what you can do is this. You can answer the next question. I got it wrong. I got it wrong. I have no idea why I got it wrong. 3.7 seconds. Oops, that's embarrassing. Okay, so I got the time wrong. It takes 3.7 seconds to fall 67 meters. Really? What did I do wrong there? Okay, I did something wrong. And then you work out the horizontal velocity and the vertical velocity. Now we've got our two velocities. There they are. Now, what we can do is to find the magnitude and direction of the velocity just before it hit the ship. Well, our vertical velocity is 40.5 meters per second. Our horizontal velocity has stayed at 36.3 meters per second, like that. So this is the actual velocity, which we calculate by Pythagoras' theorem, because horizontal and vertical are at 90 degrees. So we get whatever value we get, and that goes in there. But what we have to do is also add a direction. Now, nearly always they remind you that it is not just the magnitude, you have to do a direction. So you can do that. 10 to the minus 1, 40.5 over 36.3, and you get an angle, and you can say, I don't know, whatever it is, 61 degrees to the horizontal, whatever it is. Okay, so you can work it out, but you must say either show what it is on your diagram or write where it is in your answer. You could do to the vertical, doesn't matter, 'tis your choice. Okay, so that is adding vectors. Okay, you can do it by scale drawing if you like. So all these are adding vectors by scale drawing. And I don't particularly want to go through all of them because I want to finish off with resolving forces. Now, adding forces is where you take two or more. Adding vectors, is when you take two or more vectors and draw one after the other to find out what the resultant is. Okay, so here I can take as many vectors. Let me have 5 vectors, who cares? And I can draw them wherever I like that. And there we go, so my 5 vectors. And the resultant is we slide one over there, then the next one over there, then the next one over there, then the next one over there, and that is my resultant. Okay, so that's how we can do it for more than one. But resolving vectors is when you have one vector and you split it into usually 2. I'm going to say always 2. So we are going to start with one vector and we are going to split it into 2. So that's the other way around. The other way around is we had 2 vectors and made it into 1. This is we are given 1 and we are going to make it into 2. So at GCSE, we kind of did this. Okay, you are going to take your, there it is, a single force can be resolved into two components acting at right angles. Now, at A level, we're sticking with that. Doesn't go any further than that. Our forces are usually going to be at right angles. And the two forces, two vectors, are going to add up together to give that original single force. So let's just kick off with remembering what a vector is. Okay, in maths, it is represented by a column vector. So there is my column vector A, which is, no, there's my vector A, 1, 2, 3 across, 2 down, 3 minus 2, whichever one that is. I can't see. My thing's in the way. I think it's the third one along. That is what the column vector is. We are turning A into a horizontal bit. Where's my pen gone? We are turning it into a horizontal bit and a vertical bit. Okay, so what we are actually doing, what we did at GCSE maths, is we resolved our forces. So we could say that the vector A is equal to 3 that way and 2 that way. Now, because they're vectors, could be forces, could be accelerations, could be whatever. Okay, any vector quantity. Now, up in the top there is a snippet from the AQA specification. It tells you what they are. Okay, so if that is F, and that's just checking that this is working, and that is theta, then our horizontal component, the pink one, is F cos theta. It works, thank goodness for that. I should have checked it earlier. And the vertical component of F is F sine theta. Cheeky bit of trig, dead simple. Okay, that's what we're going to have to do. But drawing that triangle is sometimes quite tricky. So there is my vector A. I'm going to, just for the sake of it, turn it into that. I'm hoping you can see why. Because it's vertical. Could be a weight, see? That's why I did it. Now let's have a look at another one of these things. Let's have a look at this one. There it is. So I've arranged it so that the first angle, the sort of bluey lilac-y one, is 60 degrees, and the second angle is 30 degrees, and the pink force is vertical. What a surprise. Those forces are perpendicular, because that is what you are going to do. So the components, and what I've got is I've got that one pink force. That's it. That's the force, the single force. But what I'm going to do is to split it into two perpendicular components. This is what I do in my head. I slide one down like that. I slide another one like that. And then I create the triangle like that. That is my first component. And that is my second component. In my head, that's what I do. That's what I do. I slide them around to give me that parallelogram of forces like this. So I slide that one down parallel to the blue. In my head, I slide one across parallel to the red, and I get myself a rectangle. Then the length of that side is the first component, and the length of that side is the second component. Utterly foolproof. Now let me show you. I hope you got that. I hope you got that. Let me show you why I did that. Let me show you why I did that. Because I've done that. Because hold on a minute. Normal. I just want to spend a few moments looking at that word normal. Okay, so in AQA, this is what we're doing. This is what we're doing. What does that normal mean? Well, The normal, you will remember when you did your reflection in year 8. You drew a normal to the mirror. Could be curved mirror, who cares? You drew a normal to the mirror, which was perpendicular to the mirror. Okay? And whenever you did it, say you were doing refraction, your normal was at 90 degrees to the boundary. There it is. That line, the dotted line, is called the normal. Now, in the same way, a body, anything sitting on a bench like this calculator, has got a normal reaction force. If it wasn't, I'm not going to do it because I might break it. If it wasn't, its weight acting downwards would make it accelerate downwards and it would hit the floor. But if it is stationary on the bench, then Newton's first law says that there is no resultant force acting on it. So here I've got W acting downwards, and because of that, I have an upwards force, which I'm going to call the reaction force. The normal reaction force is always at 90 degrees to the surface, because it is a normal reaction force. That's it. So now I'm going to make life a little bit more complicated, and I'm going to tip this thing up. Who cares? The weight is acting downwards like that. The normal reaction force is going up like that. Now, if this body is moving at a constant speed, and please say that it is, look in the question for stationary or moving at a constant speed, then you know Newton's law tells you that there is no resultant force. So if it is stationary, then there's a frictional force acting up the slope like that, trying to stop it going down the slope. Or if it is sliding down the slope, there's a frictional force opposing that in the opposite direction, equal and opposite. The resultant force of those three forces is 0. That's a diagram that lots of people struggle with. Vertical, perpendicular to the surface, along the surface. Okay, so I'm going to have a look at this. I'm going to look at one of these Java things again. Okay, and it is going to show us the forces acting on a body on an inclined plane. So let me go back and find the inclined plane. Here it is. So here it is. Right. Boom. So up the slope, I am dragging at a constant speed a block like that. There it is. It is going at a constant speed because I am pulling it with that spring scale, measuring off the force as you might have done in year 7. If I show the forces acting on it like that, the green force is the force pulling it up. The blue force is the friction. The pink force is the weight, and the brown force is the normal reaction force. Okay, so what we can do is go back to our little diagram here and have a look at the forces acting on it. If we have this, there is the weight. There is the normal reaction force. Now, I'm trying ever so hard to draw them, because what I'm going to do now is to find the resultant of those two by drawing a parallelogram. Oh, look, it's as if I cheated. There it is. So there is the resultant force. So that's the resultant force of the normal reaction and the weight. So if I scrub that, and if I exert a force up the slope, which is equal and opposite to that, then those three forces, just like that force board thing, they are going to form a closed triangle. They are going to form a closed triangle. Why bother repeating it, Brian? That was embarrassing. Okay, that is in equilibrium. That body will either go up the slope at a constant speed or it will remain stationary. Because friction's holding it up. Okay, that is a diagram there. Now, I'm thinking, let me just have a look. Let me think. I'm thinking of, let me just go on for a couple more minutes. So I'm scared of heights. I didn't want to paint my window. My mate Toby did. So he climbed up the ladder like that. Now, notice that at the top of the ladder, there is a wheel. Okay, like that. The ladder can roll up and down the wall with no friction. There is nothing stopping it sliding up and down against the wall. Nothing whatsoever. Now, Toby is quite happy to paint the window. He's not bothered at all because he knows that is safe. Now, in an exam question, which looks like that, that is important because of that angle there. Now, if the resultant force is at 90 degrees to the wall, that means that there is no component of the resultant in the vertical or a vertical direction, which means that there is no friction between the wall and the ladder. If the ladder was being held up with a force like this, if the force was going up, say, at an angle like that, not at 90 degrees, then what we can do is we can break that force down into its components, both horizontal and vertical. Let me do that. Bom, 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 bom. Let me do it in black. I think that might be easier to see. I'll do it in pink. So that is the vertical force, and that is the horizontal force. Now, because there is a vertical force, that must be due to friction between the ladder and the wall. But because the resultant force is at 90 degrees, then there is no friction between the ladder and the wall. Okay, so slightly tricky where you have to apply that knowledge to a question, but hey, that's A-level physics, and that is why it's so much fun. I'm just going to do that. Absolute classic question. I'm going to come back to that on Friday because that is such an important thing. Comes up again and again and again and again and again. So I'm going to make sure we're happy with that. But I'll do that on Friday, bit past 9 o'clock. So I'll stop there. Any questions? By all means, stop at the end and ask. If not, bye. Have a lovely evening. See you on Friday.